Hello! In this video we're going to write a post-ordering label of the binary tree. Post-order traversal and mark the nodes of the tree with the label of this post-order traversal. So we have this tree data type which represents a binary tree. We have this tree example and we have these three types. The type for position of the, actually this is the label of the node in the post order position, and count before type which represent how many nodes we count before this node, and the total which represent the total number of nodes in all the tree. So let's define our function. I will call it post order. It takes as a first argument, it takes count before how many nodes it we count before this node, and as the second argument it takes some battery of type A, and as a result it produces as a tuple. The second element of the tuple is total type, and the first argument is a battery type which contains this A itself and position in post order. So let's write definition. Post order: if we take empty tree, no matter what the start, how many we count before, we must return a pair which contains empty tree and 0 nodes, because empty tree has 0 nodes. But what if we have not empty tree? What if we have some node which contain A, L and R? Left subtree, right subtree, and A node is node value itself. So in this way we we need to construct a pair. So the second argument of this pair is total. But what the first argument of this pair? The first argument of its pair, of course, is a tree which we created in node constructor. And as a second argument, as a first argument of this node constructor, we need to provide a pair with A and some position. Also we need to provide left subtree I will call it new left subtree and new right subtree, okay? And here we need to construct a position, actually the label of the post order. And the label of post order actually it will be how many nodes we had before this node. We can see that we have all the nodes from the left and all the nodes from the right subtree. We need to count them and then add 1 to mark the node itself. So we will write a 1 plus okay. I will take I need to Okay, I will call them nodes left. It's too long name. Okay, I will define the CL, count from the left and count from the right. Okay, and I need to define these names. I need to define the NL, and I need to define NR. NL is postorder which takes, and what the number goes to the left. If you go to the left subtree, I think they pass the n itself, because the node itself goes to the right, and the right subtree also goes to the right, and we didn't need to count them. And we need to count only the n which we get from the level above. And of course we need to pass a left subtree. And also for the node from the right, from the tree at the right, we need to pass n, and we need to pass, and we need to summarize this with the count from the left side. Yes, count from the left side. We does not need to +1 here, because nodes go to the right and it doesn't count it. And we need to pass right subtree here. Okay, I think this should work. And how can we define total? Okay, let's define count of left. Count of left is actually the second of NL, because we have it here, and we need to take a second of NL. And the count right is second of NR. And of course, here we need to take not NL, we need to take first, because it is a pair, and here we need to take first. Is this correct? Is this correct? Okay, I think this is not correct, because I forgot to add. Also, I need to add the nodes which I get from the level above here. So we actually the position of this position of the node which we unpattern match, it's summarized from all the left subtrees, all the right subtrees, from the one which goes from node itself, and we need to count all the nodes that was printed before at the left, and define this value. So I need to define a total. total is 1 plus CL plus CR. So we have node itself and all the nodes from the left and all the nodes from the right, and this is a total. And you can see that this exactly the same as this, so I can take n plus total here. Okay, and this I think this should work. Let's check. Let's try to load our model. Postorder. We can see that it compiles, and now I try to postorder this tree with our function. If I do all correct, it must postorder the nodes. Let's try postorder. Before we start, we have 0 nodes, and we start with our tree. Okay, node A has a label 7, and this is correct because we have 7 nodes in our tree. B has the label 3, and this is correct, this or not? Yes, this is correct because under the B we have 2 nodes. We have D and E under the B, and so B will be a free label 3, and so on. I think this is a correct order. But let's write a classical postorder and compare our results. So how can we define classical postorder? I will call it C postorder. If we have an empty tree, we produce an empty list. If we have tree constructed in a node with A, L, and R, we call our C postorder to the left, concatenate this to our C postorder to the right, and concatenate it with the node itself. I think this should work. Let's try it. So postorder TR, and let's you can see this postorder in the classical manner. And now let's check it with our labeled postorder. A has 7, B has 3, D has 1, E has 2, C has 6, F is 4, G is 5, and we have 7 nodes. I check this tree, and this is the correct postorder. So guys, thanks for watching. Push like button, push subscribe button, write comments, and see you in the next video, guys. Bye.